In this video, we will see about the different types of inverter, and in that we will see the operation of single phase half bridge inverter. What is an inverter? Inverter converts the DC input voltage into AC voltage at the desired voltage and frequency. Why do we need an inverter? Because we cannot store the AC power, but we can store the DC power in batteries. So the stored DC power can be converted to AC using an inverter, and we can use the AC power. So let us see the applications of inverter. So this is a house powered by solar panels. So this solar panel produces DC output which will be converted into AC using this inverter, and this AC can be used to supply the loads connected in the house. Similarly, if you take an electric vehicle, we know that battery is the major source for the electric vehicle. So this battery power, which is DC, is converted into AC by using this inverter, and this AC will drive the AC motors used for the vehicle. Basically, there are two types of inverter. One is the voltage source inverter and the other one is the current source inverter. So, voltage source inverter means the input voltage is almost constant, or it has a stiff DC voltage. Whereas in current source inverter, it has a large impedance in series with the DC source. So, this acts as a current source. In this video, we will be seeing about the voltage source inverter. So let us see the features of voltage source inverter. It has a stiff DC input voltage and it has negligible impedance, and the output voltage is independent of the load. That is, irrespective of the load which we connect, always the output voltage will remain the same. Now let us see the types of voltage source inverter. Two types are the single phase inverter and three phase inverter. In single phase you have two types, half bridge inverter and full bridge inverter. In three phase inverter you have two modes of operation, 120-degree mode and 180-degree mode of conduction. So in this video we will be seeing about this half bridge inverter. So this is the circuit diagram of a half bridge inverter. You have only two thyristors connected in series, and each thyristor has a diode in anti-parallel. And you have a split DC power supply Vs by 2 and Vs by 2, between which the load is connected. Now when we give the gate pulse for thyristor T1, so this is the gate pulse for thyristor T1. The current flows through the thyristor, load and the supply. Now you apply the Kirchhoff's voltage law. We can see that, so this is conducting, so this supply voltage will appear across the load. So V0 is positive here because I have taken this as plus and this as minus, and current direction is from A to B. So if we consider these two cases as positive, for when T1 conducts, V0 and I0 are positive. So we can draw the load voltage. V0 will be equal to Vs by 2. Now if you apply the gate pulse for the second thyristor T2, this is the circuit when T2 conducts. So the current flows in this way, and you can see that the plus end of the load is connected to the negative of the supply. So what happens to the output voltage? It will becomes negative because plus is connected to negative. Similarly, if you see the current direction, current flows from B to A. Again it is opposite to the previous case. So current is also negative. So when T2 conducts, both voltage and current are negative. And if you see the total time period T, if you change this time period, the frequency of the AC waveform changes. Suppose if I want a 50 Hz AC supply waveform, I have to turn on T1 for 10 millisecond and turn on T2 for next 10 millisecond. So if I do like this, I can get a 50 Hz AC supply. And this is the I0 waveform. Because it is a resistive load, V0 and I0 will be in phase except magnitude alone changes. And one more thing here is, it is a R load, so there is no use of this feedback diode. So this diode will be useful when you have a non-resistive load. That is the inductive load or RLC load. This diode will be useful. In case of R load, it doesn't have any purpose. So this is the inverter output voltage waveform. You are getting a square waveform which is a periodic function. So what does an Fourier series do? It can be used to represent a periodic function in terms of sine and cosine component. We want only this sinusoidal component, the fundamental one. So Fourier series helps to identify this fundamental component, and it also shows what are the harmonics present in the waveform. If you take a square waveform, so many harmonics will be there in addition to the fundamental component. We want only this fundamental component. We want to remove those harmonics. So that can be easily identified by using a Fourier series. This will give you what are the harmonics available. So we can design a filter accordingly and eliminate the harmonics and use the fundamental component. So if you see the Fourier series, f of t, this is the general one, f of t is equal to a naught plus sigma n equal to 1 to infinity. One function is there. So what is this a naught? An and Bn, they are called Fourier coefficients. So a naught is a constant, it is a DC value, so it is a constant term, and this a naught is given by 1 by t integral of 0 to t f of t into dt. Similarly, for an and bn, formulas are there. So this is the general Fourier series. Now we will apply this for our inverter output. We have seen that there are three Fourier coefficients, A0, An and Bn. It is not difficult to find all the coefficients, because if we know the symmetry of our waveform, we can easily find the coefficients, because if the waveform has some symmetry, coefficients become 0. So first we have to identify what type of symmetry our waveform has. So if you take odd symmetry, the best example is sine wave. So if you take the vertical axis, here you have positive and here you have negative. Both are similar, but this is plus and this is minus. So it is called an odd symmetry. And if you see a even symmetry, best example is a cos wave. So cos wave starts at maximum value, cos 0 is equal to 1. So this type of waveform you will get for a cos wave. So here plus and here also plus. So in this case we call it as a even symmetry, or we used to say f of t is equal to f of minus t. So in that case you have even symmetry. So now you can identify what type of symmetry our inverter output has. So this is positive, this is negative. So here if you see along the vertical axis, here it will be surely a negative waveform. So our waveform exhibits odd symmetry. And you have half wave symmetry and quarter wave symmetry. So what do you mean by this half wave symmetry? You take the total time period this half is equal to this half, then it is called a half wave symmetry. So this waveform, inverter output waveform, satisfies odd symmetry as well as half symmetry, so it is called quarter symmetry. If any waveform satisfy even symmetry and half symmetry, then also it is called quarter wave symmetry. So in our case it is odd quarter wave symmetry. So inverter has odd quarter wave symmetry. So if you have odd symmetry, only odd harmonics will be there. Even harmonics will become 0. Okay. And moreover, this coefficients A0 and AN will become 0. So don't ask how you are getting this one. You apply in the formula, you will get only 0. Okay. So you can apply and verify it. You will get A0 and AN is equal to 0. So you can remember that in an inverter which produces this square wave output, only odd harmonics will be there and only Bn term will be there. A0 and AN will become 0. Only Bn will be there. So next we have to find what is Bn. So we have seen that f of t is equal to this one. So now we will make this a0 term 0, an term also 0, and we have seen that only odd harmonics exist. So instead of n equal to 1 to infinity, I can write it as n is equal to 1, 3, 5 infinity, because even harmonics will be 0. So you write the so we can write is equal to n equal to 135 to infinity Bn sin omega t. We will find what is Bn. So Bn formula, you write it. So total time period is 2 pi, half of that is pi. So applying the limits for 1 half cycle. So f of t, this function is magnitude of this one, Vs by 2 into sin and omega t into d of t. So if you substitute integrate sin omega t, you will get cos and omega t. So substitute the limits. So when n is odd, you will get Bn equal to 2Vs by n pi, and if n is even, you will get Bn term as 0. So you can apply n equal to odd alone, because we have applied n equal to odd. So f of t is equal to, you will get this function. So for half bridge inverter, your output voltage is this one. Now let us find the performance parameters. So V0 of t is equal to n equal to 135 to infinity 2Vs by n pi into sin omega t. Now apply n equal to 1. You will get this fundamental component plus, because this is a summation sigma, so plus 2Vs by 3 pi. Instead of n, you substitute 3 omega t, then 5 omega t. So this corresponds to third harmonic and this corresponds to fifth harmonic. So this one is the fundamental component and all these things are harmonics. And if you find the peak value of the fundamental component, so this is the red color waveform is the fundamental component. If you find the peak value of this, so this is of the form Vs is equal to Vm sin omega t. So Vm means this part, 2 Vs by pi is the peak value of the fundamental component. So this magnitude is 2 Vs by pi, but square wave magnitude is Vs by 2. So this magnitude, fundamental component magnitude, will be greater than the square wave magnitude. That's why we used to draw the sine wave greater than the square wave. And if you see the RMS value of the fundamental component, Vrms is equal to Vm by root 2. So this is the peak value, that divided by root 2. that will give you root 2 Vs by pi. Okay. And Vrms is equal to, for a square wave, directly you can write it, that is the magnitude will be the RMS value. Even if you substitute and find everything, you will get again only the magnitude of the wave for square wave alone. So V0 1 RMS is the fundamental component RMS value which I have seen earlier. Then let us see the total harmonic distortion of the waveform. So we want a sinusoidal waveform, but we get only a square waveform. So surely THD of the waveform will be very high. So what is THD? It is the measure of harmonic distortion present in the signal. So THD is equal to Vrms square divided by fundamental component Vrms square minus 1. So square root of that, you can find you are getting some 48.4 something. So independent of this term V0 RMS by V1 RMS, it will be independent of the magnitude of the voltage. So if it is a square wave, you will get 48.4 percentage THD. So it is a very high value. So this is not an acceptable one. That is why when you give this type of input to the fan and tube light in case of a home inverter, it produces such a poor performance, or you will get more noise. So because of this high THD. Next we will see about the half bridge inverter feeding inductor load. So when you have an L load, you should remember one thing: the current through an inductor cannot change its direction instantaneously. That is why we always use a anti-parallel diode. And in case of L load, I0 will lag V0. That also you should remember. So you have to remember that inductor cannot change its direction immediately, and I0 will lag V0. So if you take a inverter with L load, so when T1 conducts, current flows from A to B, and when T2 conducts, current flows from B to A. So it cannot change its direction immediately. So the diodes come into action. So when T1 conducts, so this load end will be positive. So apply Kirchhoff's law. So this plus will be connected here. So output voltage is positive, and current is also, current flows from A to B. So it is positive. When D1 conducts, what happens? The output voltage will be connected to positive only. So output voltage is positive, whereas current flows from B to A, so that the current flows through D1. So current is negative. Similarly for T2, current flows from B to A, and voltage, this plus will be connected to negative end. So negative voltage, negative current, and D2 current flows from A to B. So current is positive. So now we will see the output current waveform in case of an inductive load. So this is the voltage waveform, and the current waveform should lag the voltage waveform in case of L load. And this is a L load, and you are applying a DC voltage across the load. So the current will be a ramp waveform or a triangular waveform you will get. If it is a RL load, you may get a exponential waveform. So if it is a pure L waveform, L load, you will get a triangular waveform. So when both are positive, T1 will conduct. Voltage and current positive, T1 will conduct. When one is, that is voltage positive and current negative, you will get D1 positive. D1 will conduct. So similarly, D2 and T2 conducts based on this. So next is the RLC overdamped circuit. So this is similar to the L load or RL load case, where when the T1 is conducting, the current flows from A to B. Suppose if T1 is turned off, the current has to be flowing in the same direction. It cannot change its direction immediately. So it continues to carry the current through the diode D2. So current will be flowing through the diode D2. So after T1 is turned off, D2 carries the current. And when this current becomes 0, when the current through the diode D2 becomes 0 and it gets turned off, T2 will carry the current in opposite direction. And when T2 is turned off at this time period T, the current is flowing in this direction. So the diode D1 will come into action and it carries the current. So D1 will carry the current. So this table remains the same. You can check it. So for D1, plus voltage minus current, plus voltage minus current. For T1 plus plus, so plus plus, so minus plus is D2 and both are minus is T2. So table remains same, voltage waveform remains same, only the shape of the current waveform changes based on the values of R, L and C. Next is an underdamped circuit, same thing, but the only difference is here is that when this capacitive reactance Xc is greater than XL, the current will lead the voltage by an angle phi. So you can see here the voltage starts here, whereas current waveform starts here. So the current is leading the voltage waveform. So the sinusoidal waveform is like this. So here itself the current becomes 0. So this is T1 time period. So both are positive. So T1 and one is positive and current is negative is D1. Same table, same voltage waveform. Only current is leading the voltage by an angle pi. So in this case, you can see that T2 is turned on here only, whereas T1 is getting turned off here itself. It means that in this case, there is no need for forced commutation circuit. The thyristor gets turned off by the load itself. So load commutation occurs in an underdamped circuit. Otherwise, you have to, so whenever you have a DC source, you have to go for forced commutation. But in case of RLC underdamped circuit, sometimes because of the nature of the load, the current becomes 0 before the next thyristor is turned on. So in such cases, natural load commutation occurs. So if you see the limitations of half-bridge inverter, you need a 3-wire DC supply. So that is the major limitation and it has a very few applications. This half-bridge inverter we are analyzing so that we will understand the full-bridge inverter and 3-phase inverter easily. So the points to remember here are in voltage source inverter, the output voltage is independent of the nature of the load that we have seen. That is, for all type of loads, output voltage waveform remains the same, only the current waveform changes. Inverter output, only odd harmonics exist in the inverter output because of the symmetry of the output waveform. And the magnitude of the fundamental component is greater than the magnitude of the inverter output voltage. That is, the sine term which we draw is greater than the square wave output. And the THT, total harmonic distortion, is independent of the output voltage magnitude. If you need the study material for this one, you can visit this website, and if you like the video, do subscribe to Read Electric Vehicle channel. Thank you.